Jai Hind everyone. I am Kajal Kaushal, Assistant Professor from the Department of Information Technology, Ajay Kumar Garg Engineering College. Today I am here with my video lecture that's about the Control Unit Microinstruction and all about the instruction cycle. Many of the students face many difficulties understanding how actually the instruction is fetched, decoded or executed from the memory or destined registers. So here I am with my video that will be most probably explaining you the detail and will help you solve your problems and help you understand the instruction cycle. So without further ado, let's get started. So instruction execution cycle consists of these 5 steps: fetch, decode, execute, and memory access as well as the write back. Whenever there is the instruction that is to be fetched from the memory, the processor needs to fetch that instruction and then as per the requirement, it's decoded. Then finally, the operands are being fetched from the destination. It may be register or it may be the memory, and then it is executed. After the execution, it can be stored in the memory, that is, it can be stored, written back to the memory, or it can be just placed for a temporary being in the register. So here it is. Here is the overall process of the instruction cycle. First, after the initiation, it's being fetched, then decoded, then the address is being reached if it is not direct, and then it is executed. So, over and all, there are these phases that consist of the part of the instruction cycle. So, we say the instructions of the program that are carried out throughout the process is called as the instruction cycle. The instruction is fetched definitely from the memory. We need to fetch, the processor needs to fetch the instruction from the memory. Instruction is definitely of the format that we have discussed prior in the previous video. After that, the instruction format needs to be decoded as to what is the operand. The operand needs to be searched for. That operand may be directly stored in the instruction, as I discussed in my previous video, or it may be in some register, or it may be somewhere in the memory. So it needs to be decoded. It needs to be understood that where exactly operand lies. So the effective address needs to be calculated so that the operand can be fetched if the address is indirect. If it is direct, then it can be fetched right from that instruction only. After that, the instruction is executed. Now, the computer instructions are of 3 types. Depending upon the format, by looking at the format, we can very well notice that whether the format is referencing to a memory, or it is referencing to a register, or it is about the input-output format, that is just considering the peripherals of the input-output devices. We will see how we can say that the instruction belongs to which of the following format. So, over and all the instruction, we need to see what is the opcode. Depending upon the opcode, the 3-bit opcode decides whether it is of the memory reference format or it is of these two, the register reference or the input-output. Once we are done with this identification, that whether it is memory or these two, after that, further by looking at the last bit, we can say whether it belongs to the register reference or to the input-output format. For this, we need to identify the opcode, we need a decoder, of course, so that it could be very well identified which of the following format is there. So, this is what I was talking about. The instruction consists of these 16 bits, where 0 to 11th bit denotes the address, okay. It may be the address somewhere in the memory, and after that 12, 13 and 14. This is the opcode. The last bit, that is the 15th bit, that is the 16th bit. Here I have written 15 because generally in our computer digital system we start it's a nomenclature that we follow, that we start from the 0. Okay, so this 16 bit will be represented starting from the 0 and ending to the 15. The last one, that's I, will tell us, in the case of memory reference instruction, this last bit will tell us whether it is direct or it is indirect, depending upon whether its value is 0 or its value is 1. But now, when the opcode starts from 000 to 110, that is 0 to 6, 0 to 6 will be pointing out to the memory reference instruction. Just discussed in the previous slide, the opcode from 0 to 6 will tell us about the memory reference instruction. And once the opcode is 7, that is the decoder 7, D7, then we can say that it may be register reference or it may be input-output instruction. See, here also 12 to 14 is 111 and here also 12 to 14 is 111, that is 7. Okay. Now, how we are going to identify whether it is register referencing to a register or it's pointing out to the peripherals? This can be seen by the last bit. If it is 0, that means it is pointing to the register reference, and if it is 1, then it means it's the input-output instruction. So, in this way, we can identify, the processor can identify whether the instruction is memory reference, register reference or input-output reference. This whole cycle we will be discussing in this video only, how the fetch decode is done. So, let me first discuss the flow chart for the instruction cycle. Once the instruction cycle, that means the instruction format, how are we going to identify the memory reference or the input, output or the register. So, starting from the first one, and here these T's are representing the time sequence. The sequence counter, it starts from 0 and initially it starts by the value that is there in the program counter. The program counter points to the points to the next instruction. So, whatever program counter value is having with it, that is the instruction that needs to be fetched by the processor from the memory. So, first of all, it needs to fetch the value that is there in the program counter. This program counter will give that value to the address register. Finally, from the address register, the way the format is being divided, this value, this memory, the memory word of the address register, that is whatever value the address register is consisting of, that will be given to the instruction register. And at the very same time, at the very same instant of time, that is the same clock cycle, that very same moment, the PC, that program counter, will also be added by 1. That means it will now point to the next instruction. This is the rule. After that, the decoding. This was the fetching process. After that, the decoding is being done. For that, we need to understand what was just discussed in the previous slide. That is, the 12 to 14 bits will tell us whether it is pointing to the memory reference or to the register reference and input output, and these 0 to 11 bits are the actual address that needs to be, either it will be operand directly or it needs to be fetched from the memory or a destined register, and this will tell us about the direct and indirect addressing. So, once we are inside, if the decoder value is 0, that means it is pointing, decoder value is 0 means either it will be D7 value will be okay, it will be 1, that means 111. If it is 111, then it can be register or it can be input output. This is the case for 111 D7, and this is the case for 000 to 110. If it is 000 to 110, then it will be definitely the memory reference. Once it is memory reference, then we need to see the last bit, that is the 16 bit. If it is 0, that means the value is direct. It's the direct addressing. We can just fetch the value and we need not do anything. Just that value needs to be used by the used for the execution. That's the operand itself. Okay, and if it is 1, that means it doesn't hold the actual value. It is having the address for that value to be fetched. So again, this value needs to be brought from somewhere, the destined register or from the memory. So as we are into the memory reference side, that means it needs to be brought from the memory. From here, the memory word will be sent to the MDR via the memory address register. Okay. Now coming to this side, if it is D7, in that case we have two referencing. Either it may be register or it may be input output. Again, if the value of I is 1, then it will be input output execution. If the value is 0, then it will be register instruction execution. Okay. And again, after going through all the processes, once again the sequence counter will made to be 0, so that it can start fetching the next instruction again. For this, we need to understand there are two concepts, pipelining and non-pipelining. If the system is following the pipelining approach, then once the decoding of an initial instruction is being done, at that instant of time, the second instruction will start fetching, and likewise the overlapping of all the phases will be done. That will speed up the process. So this is the pipelining approach. At this very same instant of time, there is another concept also, that is of the interrupt. Interrupt is, we are incrementing the program counter by 1. That means we are considering that our steps are going through in a sequence, step by step. But it never happens in this way. Many a times, there are some branching instruction, there are some jumping instruction. That means not always the instruction is following the same path. It can be interrupted by some hardware or some software interrupts. In that case, our program counter may not be searching for the next instruction in a sequence. It will first execute the instruction that needs to be executed as per the priority, and then only it can come back and restart the sequence that was going on. Okay. And anyway, whenever the instruction is being executed, finally the sequence counter will be made 0, and once again it's ready to start with the next fetching part. So in this way, the whole instruction cycle works. Okay. So this is the way the fetching phase is done. The program counter, it provides the address and the instruction is fetched from the memory. That particular instruction is placed to the instruction register. It's very simple. Seems to be complicated for the student, but actually it's not that much of complicated. Control unit then decodes the instruction. As we have just seen how it decodes the instruction, it divides the whole instruction into 3 parts. One part is the opcode, the another part is for the address, and the third part is for the direct or the indirect addressing. When it identifies the opcode and the operands, it just prepares the control signals as to which particular memory or which particular signal needs to be started. In the execution phase, now comes the role of the arithmetic logic unit. And the completeness of the arithmetic logic unit lies in the scene that it needs to perform all type of operations. It can be logical, it can be arithmetic. If the ALU is performing all the sorts of executions, all the sorts of operation, we say that it is complete. Else, it's not. Okay. And the registers provide the input values. Finally, the result is computed and it is sent to the memory to be written back or to the destined register. When the memory is being accessed, then it means that not only the register, there is a requirement of the memory. Memory unit is being required. Not always the memory unit is required. Many a times the instruction is having the operand itself or the register is also having. So this is the case where, one thing I want to clear, it's not always that written back it needs to be done. It's just a part. We can have this phase or we cannot, depending upon the type of the instruction we have. Okay, now we can see the example with this. Add R3 and R1. Here R3 is written inside the bracket. This means that R3 value is not having the operand. It's having the address. This bracket signifies that it's indirect. It's not having the actual value. It's having the address of the register where the value is to be searched for. So, we need to fetch the instruction first. Okay. That instruction, that means somewhere the value is there in R1. It needs to be added to the value that is having the address in R3. Finally, when the value of R3 is being fetched, that value is being added to the value that was in R1, and finally this value is stored to R3 itself. Okay. Or we can also say that this value can be stored into R1 finally. Okay. So we can start from the left hand side. That means to the value of R3, add the value of R1 and store that value in R1 itself. Okay. This is the way it's being written. Okay, now for the example that we have taken, that add R3, R1, we will see how this whole process works. This is the case of a single bus organization. Here a single bus is there and it's having all the components that we all know. For example, it's having the PC, that is the program counter, memory address register, memory data register. There is a multiplexer. This is the arithmetic logic unit, and there are some. There we can also see the general register organizations having the register starting from R0 to Rn-1. We are also seeing that here we have temporary register. We are also having seeing that there is a register Z, register Y. These all are the registers that are having some of or the other temporary values that needs to be given to the bus. This is the single bus organization. And here is the instruction register, and this instruction register will send the instruction to the decoder or the control logic. And finally, from there, after being decoded, these control signals will be generated. And these control signals will help the instruction cycle to be done in this manner. This is the way the instruction will be done, and we are going to see how it happens. So first of all, we need to fetch the instruction. For that, first the program counter will send the value. The first step is that the processor will look for the value that is inside the program counter. This program counter will send the value to the bus. Okay, this value following the path of the bus, this is the data path that is being followed in the single bus organization. This value will send the value of the program counter to the memory address register. This memory address register will be having the address line, that is the address bus. We all know there are three types of buses: control bus, address bus and data bus. By using the address bus, it will move towards the memory unit. From that memory unit, the value that was inside the address pointed out by the program counter, that value will be sent to the memory data register. And this data register will again use this bus to give the value, to provide the value to the instruction register. Now, meanwhile, what happens? This program counter also needs to be updated. Now, we consider the byte addressable memory. When we consider the byte addressable memory, that means if it is of 4 bytes, then every time, for example, starting from the value 1000, since considering the value of program counter was 1000, then considering it's a byte addressable memory of 4 bytes, the next value will be 1004. So, our program counter needs to be updated at the very same instant of time. That means the same instant of time where this value was being given to the MAR, at the very same instant of time, again this value will be sent to the arithmetic logic unit to be updated by the value 4. That means this value needs to be incremented by 4. So that means this value when comes here, the program counter will send its initial value to the register Y. This register Y, how it goes inside the register Y? At the same instant of time, the Y value is being dominated so that there is a switch, and this switch will make the value of Y is equal to 1. That means here the value can be entered by the bus. This value will move here, and this value 4 is also given to the multiplexer, and in this way the value of the program counter will be incremented by 4. This value will be sent to the Z register, and this Z will give the value to the bus again, and again this value will be given to the PC, that means program counter. The program counter will have the value that is being given by the Z, and this program counter will be incremented by 4. Okay. So, these two processes are happening in parallel. Now, come to the previous process. Here, by the time the value of the memory address register moves to the memory bus, it gives the value to the memory data register. Memory data register will give the value to the bus, and via this bus, it will move towards the instruction register. This instruction register knows that it needs to fetch the value or fetch the whatever data is inside the register R3 via the control logic. It needs to understand, it will understand that it needs to fetch the value from R3. Again, it will follow the same path, and somewhere it will locate the value R3. From here, it will see that it's a address. Now, again this address will move to the MAR. This MAR will be read by the memory via the address bus. That memory will give the actual value that was lying inside the register R3 and will provide the value to the MDR. This MDR will send the value to the bus. This bus will again send the value to the instruction register. Now, this instruction register will send the value of the address that was pointed to by the register R3, and via this control logic, it will again move towards the B register. This B register will be directly giving that number to the ALU. Then we will see that there are two inputs A and B. The A input is always using the multiplexer for getting the value from the register I, so that a selected value can move inside the input A. But this B input always takes the input whatever that is given by the B. So the value of R1 will be also there in the ALU, and the value of R3 pointed to by the R3 register will be also given to the ALU. Now since ALU is having two values, two input values, one from R1 and one from R3. Okay, R3, or we can say the value that was there inside the address pointed to by the R3 register. Now the opcode, when the instruction register got the value, the overall format, at the very same time the control signal also read whatever opcode was pointing to. If it was pointing to the add operation, that means the ALU needs to add these two values that are coming inside via this A and B input. Now this added value will be given to the register Z. This register will give the value to the bus again, and from this way this value will be stored to R1. In this way the whole process gets completed. We can write the same, all the processes in this sort of action. So what happened at the very beginning? The program counter value was out, that means PC out. At that same time, at the same instant of time, the MAR, that means the memory register, memory address register, read the value that was being given by the program counter. So here it is written MAR in, it was read, and because we need to increment the program counter by 4, that means the selection was being done for 4. Here it is written constant 4, it's already there because we are having the byte addressable memory, that is we are having 4 bytes of increment. It is being added and Z in, that means the added value of the program counter is sent to the Z register. Meanwhile, that Z register will give the value to the PC again. So in the second step, it's being written Z out. That means PC value is given out to the bus. This value is being given to the program counter. So it's written PC in, Y in. Y in, at the same time, the value that was brought to Y is there inside. That value is of the instruction register, the value that was being given by the instruction register. That means R1 and R3 both are having some values. So one of the value is there inside. Okay. When the whole process is being completed, the process, that means the value of the PC that entered inside the MAR, it is being fetched, it is being searched, and the value is entering inside the MDR. This time the memory function needs to be, we need to wait for this overall process to get executed. So this written memory, wait for the memory function calculation. Okay. And finally the data is out, that means MDR out, it moves to the instruction register IR in. Then the value of R3 is read by the MAR in. See, it's written R3 out, and again the register, address register, reads the address that is inside the R3. Now the value of R1, that value that is exactly inside the R1, directly the operand is inside the R1. So R1 out is reaching Y. So that's why it's written Y in. R1 value is moving to Y register. That Y, again for the process, meanwhile the R3 value is to be calculated. We need to wait for the memory function to get executed. Finally, when the MDR value is out, that means now both the values will be added, And when both the values will be added, that will move out of the Z register. It will move to the R1 because it's destined that after the calculation of this value, it needs to move to the R1. That is, the destined register is R1. So in this way, the whole process gets completed. Whichever component is being active at that very instant of time, the value is written as 1 in the table, and whichever component is not active at that time, that's waiting, the value is written as 0. So we can have a compiled way in this table also. In this way, we understood the execution of the complete instruction by following the instruction cycle. Hope you all understand how the instruction cycle works for all these type of instructions. And if there is any query, so do comment and ask. Okay, thank you so much.